Transformations of functions. All functions can be graphed using transformations. For each type of function, there is a parent function that is the starting point of transformations. Let's look at 4 types of parent functions. First, absolute value functions. The parent function is y equals the absolute value of x. For each x, the y is its absolute value. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. The absolute value of 3 is 3. For negative numbers, the absolute values are also positive. So we once again get 1, 2, and 3. Thus, the parent function forms a V with the vertex at 0, 0. The left side of the V has a negative slope of negative 1 over 1. The right side of the V has a positive slope of 1 over 1. Now let's consider quadratics. The quadratic parent function is y equals x squared. Thus each y is the square of the corresponding x. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Negative numbers square to positive also. So negative 1 squared is positive 1, negative 2 squared is positive 4, negative 3 squared is positive 9. Thus the quadratic function also has a vertex at 0, 0. Slopes, however, are curving instead of straight. The slope continues to change. On the left side it is negative. On the right side it is positive. Thus the difference between the absolute value function and the quadratic function is the absolute value function is a V-shape made of straight lines with constant slopes, and the quadratic function is a curved shape with changing slopes. Now let's look at 2 one-directional functions. The family of exponential functions have many parent functions. As an example, let's use the parent function of the exponentials with the base 2. Y equals 2 to the x. Thus 2 to the 0 equals 1, 2 to the 1 equals 2, 2 squared equals 4, 2 cubed equals 8. Now remember that negative powers make fractions. So 2 to the negative 1 power is 1/2. 2 to the negative 2 power is 1/4. 2 to the negative 3 power is 1/8. This graph has a continuously changing positive slope. It gets steeper as it is rising to the right side of the graph. The graph never crosses below the x-axis, so this x-axis is called the asymptote. Finally, we will look at linear functions. The parent function is y equals x. Thus every y is the same as every x. The line has a constant positive slope that never changes. The slope is 1 over 1. Let's start with absolute value functions. When there is addition or subtraction inside the absolute value symbol, the graph moves horizontally in the opposite direction. For y equals the absolute value of x plus 3, the graph moves left by 3 units. The new vertex is negative 3, 0, and the slope does not change. This graph is 3 units to the left of the parent function, which is shown in black. For y equals the absolute value of x minus 3, the graph moves 3 units to the right. The new vertex is 3, 0. The slope does not change. When the addition or subtraction is outside the absolute value symbol, the graph moves vertically. For y equals the absolute value of x plus 3, the graph moves up 3 units from the parent function. The new vertex is 0, 3. For y equals the absolute value of x minus 3, the graph moves 3 units down from the parent function. The new vertex is 0, negative 3. In neither case does the slope change. When the graph is multiplied by a number bigger than 1, the slope does change. It gets steeper. In y equals 3 times the absolute value of x, the slope becomes 3 over 1. The vertex does not change. When the function is multiplied by a number less than 1, as in y equals 1/3 times the absolute value of x, the slope is 1/3. the graph becomes wider. Once again, the vertex does not change. When the graph is multiplied by a negative number bigger than 1, as in -3, it is reflected, but it keeps the same shape as it had above. So we get a slope of 3, but facing downwards. When the graph is multiplied by a number that is less than 1, but negative, the graph is reflected. It faces downwards, but it is wider. The slope is 1/3. Finally, if the graph is multiplied by -1, but faces downwards with a slope of 1. We can put all these rules together in this last example. To find the vertex, find the opposite of the number inside the absolute value and the same as the number outside. The vertex is -4, -1. Now to find the slope, use the number that is multiplying at the beginning. The slope is +3, so the v opens upwards with a slope of 3. Transformations of quadratic functions work exactly the same way as absolute functions, except that the graph consists of curved lines rather than straight lines. Start with the parent function. The graph of quantity x plus 3 squared moves left 3 units. The vertex is -3, 0. The first slope is 1/1. Then draw a smooth curve that matches the parent function. The graph of y equals quantity x minus 3 squared moves right 3 units for a vertex of 3, 0. The first slope is 1/1. Once again, draw a smooth curve that matches the parent function. When the addition or subtraction is outside the parentheses, the parabola moves up or down. Once again, start with the parent function. The graph of the equation y equals x squared plus 3 moves up 3 units for a vertex of 0, 3. The first slope is once again 1/1. Draw a smooth curve that matches the parent function. Graph of the function y equals x squared minus 3 moves down 3 units for a vertex of 0, -3. The first slope is 1/1. Then draw a smooth curve that matches the parent function. When the graph is multiplied by -1, it is reflected downwards. The graph of y equals -x squared is the same shape as y equals x squared, but opens downwards. When the function is multiplied by a number greater than 1, the graph will be narrower. The first slope of the graph of y equals 3x squared is 3/1. Thus the graph is narrower than the parent function. Graph of -3x squared is the exact same shape but reflected downwards. When the graph is multiplied by a number less than 1, it becomes wider. Thus y equals 1/3 x squared is wider than the parent function because the first slope is 1/3. Graph of -1/3 x squared is a reflection of the graph of y equals 1/3 x squared. To combine these rules, look at the last function. Notice that the number inside the parentheses is a +4. For the vertex, we will use a -4. The number on the end on the outside is -1, which we will use in the vertex. So -4, -1 is the vertex. Look at the multiplier at the beginning. It is 3. This will provide the first slope of the graph. It is positive, so the graph opens upwards. Now let's look at exponential functions. We will use the parent function y equals 2 to the x power. To move this graph 3 units to the left, add 3 to the exponent. Each point moves 3 units to the left. The graph stays the same shape and keeps the same asymptote. To move the graph 3 units to the right, subtract 3 from the exponent. Each point moves 3 units to the right. This keeps the same shape and the same asymptote, but moves 3 units to the right. To move the graph upwards 3 units, add 3 to the function, not the exponent. the asymptote moves up 3 units to y equals 3, as does every point in the graph. To move the function down 3 units, subtract 3 from the function. The asymptote moves down to y equals -3, and the function moves down with it. Multiply the parent function by -1 to get a reflection across the x-axis of the original graph. When the graph is multiplied by a number bigger than 1, as in the case of y equals 3 times 2 to the x, it becomes steeper. When the graph is multiplied by -3, it is reflected across the x-axis, but is still dilated by 3. When the function is multiplied by a positive number less than 1, it becomes flatter. When the function is multiplied by -1/3, it is a reflection of y equals 1/3 times 2 to the x. To combine all these rules, look at the last example. Start with the asymptote at y equals -1. Move 4 units to the left, and then stretch the graph by a multiplier of 3. This is how we transform exponential functions. Transformations work on all functions, no matter what. I can even make up a function and use transformations on it. We're going to just make up a little function. This will be my parent function. I'll put it in each of my graphs. To move the function left 3 units, add 3 to x inside the function rule. Every point in the function moves left 3 units. The graph stays the same shape. To move the graph right 3 units, subtract 3 from inside the function rule. Every point in the graph moves right. To move the function up by 3 units, add 3 to the function outside the function rule. Every point moves up by 3 units. The function still keeps the same shape. To move the function down, subtract 3 units from outside the function rule. The graph moves down 3 units. If I multiply the function by -1, it will be reflected across the x-axis. If I multiply the function by 3, every point will be multiplied by 3 in distance from the x-axis, so the graph will be stretched steeper. If I multiply by -3, I get the same graph, but it is reflected across the x-axis. If I multiply the graph by 1/3, every point becomes 1/3 the distance from the x-axis, so the graph becomes flatter. If I multiply the graph by -1/3, I get a reflection of the graph of y equals 1/3 times function of x. I can put these rules together to graph the last example. First, I'm going to multiply each point's distance from the x-axis by 3. Then I move each point left 4 and down 1. In this way, we can transform any function, even one we just made up. Remember, to understand transformations, the number inside the parentheses with x moves the graph right or left. This is called horizontal translation. The number added or subtracted to the function moves the function up or down. This is called vertical translation. A multiplier at the beginning stretches or shrinks the function. This is called dilation. If the multiplier is negative, the function will also be reflected. Please feel free to use these notes as you complete your homework. Thank you.